Yeah, thanks, Kai. Welcome everybody to our talk. So first a few words on the standard. I'm also co-founder of Data Artisans. You probably know, was founded by the original creators of Apache Flink. I've been with the project since day one, such as just like Stefan. We just announced the EDA platform, as you've heard in the keynote. The whole thing consists of wraps around Apache Flink, Kubernetes. It has this component, the DA App Manager, which manages the lifecycle of applications, integrates with logging, metrics, and continuous integration and deployment infrastructure. And yeah, this product was just released GA a couple of weeks ago. Flink powers use cases at many companies. We've heard that already in the keynote. So this is just a few of the companies that allowed us to show their logos. And one of the nice things of Apache Flink is that it comes with layered abstractions for developing streaming applications. So on the bottom, we have the process function, which is a very powerful abstraction because it exposes the APIs to deal with state and time, which are like the principles or the fundamentals for stream processing. So you can register timers, you can configure different types of state, how you want to interact with the state. You can you receive a record, you say, hey, I want to deal with this record in 1 hour, and whatever I receive within this hour should be, I want to handle with that. So you can do pretty much everything using the process function. If you go one layer up, the data stream API is an API that has primitives for the most common operations on streams, also common abstractions for data parallel programming, like map functions, reduce functions. You can do windowing with that. So this has a lot of the time handling already built in, so you don't have to care about that. If your use case is okay, if you're not going for very custom logic, then the data stream API is a good fit. And on top of that, there is the SQL API and also the table API, which are pretty tightly integrated with each other. The nice thing about Flink is that you can actually use all of these three things within the same program. So everything can be mixed and matched as you need it. So you can do like the easy ETL preparation work using SQL. If you have an operator that is more sophisticated, you can implement that in the process function and then glue these APIs pretty much together. In this talk, we're talking about the top layer, obviously, the SQL and table API part. And this is an example for a simple query. As you see, Flink is not implementing some kind of SQL-like API. We're implementing here standard compliant SQL. And the table API is a language integrated API, which means that you can, instead of specifying a query as a string, which is opaque to a programming language that would use it, a link style API is integrated with the programming language. In Flink, that can be the case for Java or Scala. And then you can basically define the query by method calls on something like we call the table environment. So you say table environment scan, which returns you a table object. And then on this table object, you can do things like group by, select, filter, and all these operations to compose a query. And if you look at it, you basically see that it's pretty much a little bit wrapped around than in the SQL part. So this follows more the workflow of how you would compose a data flow. You first say scan, so you get the data, then you say I want to group by it, I want to select it, and if you then would do a filter, then this would be somewhat equivalent to maybe having a having query at the end of the SQL query. So what is important about these APIs is that these are unified APIs for batch and stream processing. And what that means is that the query specifies the same result, regardless whether it is applied on a data stream or on a static set of data. So this is just standard SQL applied on a stream, or like the table API variant of it. It doesn't really matter what kind of data you have, the result will be the same. How are such queries translated? So we have the table API on the upper left, the SQL query on the upper right, and what we are using in Flink is we are built everything on top of Apache Calcite. And both queries are translated into the same logical representation. So both queries are being translated into a Calcite logical plan. So in case of SQL, we are using Calcite's SQL parser and validator. We get the logical plan. In case of the table API, we translate the API calls also in a logical query plan and get it in Calcite. And then the Calcite optimizer would optimize the query depending on whether the sources are streaming tables or static batch tables. And then we either get a data set plan if the input is bounded, or we get a data stream plan if the input is unbounded. So because we're translating everything into data set or data stream plans, this also explains why it's so tightly integrated with the data stream or data set API. So you can get a data stream back and then do all the operations that you would do on a regular data stream with it. So what would happen if we have this query here and we would run it on a file of data on a static data set? We basically have the input data here. We would just process it with the query, and then we would have a result. The input data is read at once, and the result is also produced at once. So this is just getting the data into the engine, crunching it, producing a result, and then we're done. If clicks is a stream, this is a little bit different. So if it is a stream, we don't have the full data set available at one time, right? So the data arrives over time. So whenever we get a new record, we give it, so to say, into the query and reproduce a result. So if we now say here the query says group by user and then a simple count, we get a record for a user Mary. What the query does is then it produces a result row with Mary with a count of 1, because this is like the first row that we've seen. So if we would stop here, this would be the result. We get the next row for Bob, again count 1. We get another row for Mary, and now you might have seen that we're updating the count here for Mary. So we have, as the query continues, as we get more data, we also need to update previously emitted results. And this is how we then go on. So we ingest the data over time, continuously reading the stream, and we also have to update the result continuously. But the result, in the end, is the same as with the batch query. So why is it important to have this unification of batch and streaming? So first of all, it is important to use the same syntax, so no custom stream SQL syntax, so to say, because this allows for users who are familiar with batch SQL or for standard SQL just to be easily onboarded, also running SQL queries on streams. It also means that we have the same semantics, so even if you would specify the same syntax, you might still produce different results. This is also not, and then surprising the user, either in best case he notices that the semantics are different, in worst case he doesn't even notice that something else is computed than you would expect. So having exactly the same syntax and semantics is very important for how you can actually use the API. It's also important for portability, so you can run the query on bounded and unbounded data and on recorded and real-time data, which is important if you have use cases where you want to backfill data, so some data arrived late or whatever. You don't have, we've seen the talk from the Uber folks just before this session on the main floor, and they said they often have the use case to backfill the data, and if your streaming job is implemented in Samza and your batch job for the reprocessing is implemented in Spark, well, then you have to ensure that both are doing the same thing. But if you have an API that is doing the same thing on both streaming and batch data, then you're basically good to go immediately. So, but how can we actually achieve these SQL semantics on streams? or the same semantics as on some batch data. Actually, it's not a very new thing that we're doing. Database systems have been doing that for quite a while, and the important concept here is the feature of materialized views, where you basically define a view on some kind of table, and the database system would persist this view, and then you could transparently run queries against the base tables, and the database optimizer would figure out, oh, I have already something pre-computed that I'm using in the query, so I don't have to recompute it, I'm just using the data that I have in the materialized view. So this feature is used usually to speed up analytical queries. However, a materialized view, since the data is not computed on the fly, it is persisted somewhere, it needs to be updated as the base tables change. And if you think about it, this process of view maintenance is basically very similar to running SQL queries on streams. You have the view definition query, which is the query that you want to evaluate, and then you get like changes one by one that are applied on the base table, and these now have to be incrementally applied on the result on the materialized view, on the table that is actually persisted somewhere in the database system. And so this is actually basically doing exactly the same thing. You get data one by one, updates, inserts, deletes on the base tables, and these now have to be incrementally also applied on the materialized view. So this is not something something new. However, in the context of a stateful stream processor, we're obviously also have to use different implementations, different algorithms and techniques to do that. But from a semantics point of view, this can be done. So what Flink uses this concept of dynamic tables for tables that are changing over time. So we have a table that is updated as more over time. And if you then apply a query on such a dynamic table, then the result will be, again, a dynamic table. So the result will be updated as as the input tables are updated. Exactly, basically, materialized view maintenance. However, in the context of a stream processor, you now need somehow a way to convert a stream into a logical dynamic table, and then you would apply the query on it, you would get a result dynamic table, and then you have to convert the table back into a stream if you want to have a stream in the end. There are a couple of ways to do that. The easiest way is something that we call append conversion. If you consider each record on a stream as an append to the logical table, then you get a table that is continuously growing. So this is like what I've shown in the example. For every new record, we append a record. For every new event from the stream, I append a record to the table, and then you have to update the result as if you would always get an insert into the table. There are certain queries. If you have a simple query like a filter query on such a table, the result is also a table that is just growing. Either the result is being forwarded into the output table or it's filtered out, but the result is also a table that is just being appended, and this you can then also easily convert into a stream which produces more records. There are other kinds of conversions, so the upsert conversion, for instance, where you have a certain key attribute, and whenever you receive a record with this key, you update or insert into the result table. So you simply do upsert modifications on the key of the table. And what we've seen in the result when we had this simple group by query, the result that we had there was a table that was basically also modified somehow with these upsert in an upsert manner, right? Whenever you get a new record for a user that wasn't already in the output, you would insert a new row, and whenever you got a record in the input table that was already in the output table, you would update the row. And that way you can also construct a stream that goes downstream that has this upsert semantics. And finally, the most powerful way to convert, or the most generic way to convert a stream into a table or a table into a stream is obviously the changelog conversion, where you have arbitrary modifications on the input table, upserts, inserts, and deletes. which are logically applied on the dynamic table. And then in the output, you also can basically convert any table into a changelog stream, which then has to encode how the table was changed. So what's the feature set that we're supporting in, or we will support, I should say, in Flink 1.5? It hasn't been released yet, hopefully soon. So the feature set here is simple select from where queries, so selection projection. We're supporting group by queries with non-windowed, without windows, but also with tumble, hop, and session windows in the group by clause. We're supporting joins in that are defined in windows. So you have a row for a certain time, and you want to join it with all rows that arrived with a timestamp 10 minutes earlier and 10 minutes later. So you somehow specify a window around your around the record that you want to join with, and also non-window joins. Flink has good support for user-defined functions. You can define scalar functions, aggregation functions, and also table-valued functions. And there is the Flink CLI client, for which we also see a demo later. On the streaming side, we're also supporting over windows, which is a fairly nice way to aggregate data. And all the set operations, which are a bit hard to express on streams, are currently only supported for batch. So what can you build having all of these things at hand? Well, first of all, you can, of course, build data pipelines to move data, transform it, aggregate it in real time. You can build low latency ETL style of applications, converting, enriching data, writing it into a different format, ingesting a stream from Kafka, writing it into a database system, key value store, or even a file system. Or the other way around, having files that appear over time and getting the data from there and writing it into an event log like Kafka or Kinesis. You can, of course, also run stream and batch analytics on streaming and batch data. And a common use case is also to basically have queries that maintain a materialized view in a database or key value store, such as Elasticsearch, and then have a dashboard that reads the data and renders it. So you have low latency, the latest results that you got from the stream being converted, being updated by the Flink SQL query, and the result being maintained in an external data store, and this data is then displayed with low latency. So we'll now show a demo that is centered around this New York taxi rides data set. We can actually derive a stream from this data, so it's data with a nice timestamp, so we sorted it. We removed some attributes here. We just have like 5 attributes here, like a ride ID, which is the ID of the taxi ride. We have a flag, whether this is an event that indicates the start or the end of a taxi ride. We have longitude and latitude for the pick up or drop off location, and a timestamp of when this event happened. So each taxi ride is represented by two events here in this stream. The pickup and the drop off event. And if we use this data, we can now specify queries on this. One example would be, for instance, if we have a query and we want to identify popular pickup and drop-off locations, then we could do that by specifying or by running a query on the data that computes for every 5 minutes for each location the number of departing and arriving taxis of the last 15 minutes. So if we want to compute something every 15 minutes for the last every 5 minutes for the last 15 minutes, then this is an indication that we want to perform what we call a hopping, or in CADSet this is called, we're using CADSet syntax here, it's called hopping window. In the Flink data stream API, it's called a sliding window, so there's like a mismatch in terminology, so to say. So we're using the CADSet syntax, so here it's a hopping window, so we group the table, the data per cell, because we want to group it per location. Cell is here, and an ID that we compute from the longitude and latitude using a user-defined function. So we group by cell, we group on is start because we want to distinguish pickup and drop-off events, and then we say hop, which creates a window here, and so we have this group then, and in the select query we simply say count star, and we give the cell, the start flag, and the hop end, which returns the timestamp for this particular window. If we want to compute something else, like the average write duration between per pickup location, we would have to join the start event and the end event because we want to know how long the duration of a write. We can do that using this window join that I described before. You see this here. So we join on write ID because we only want to join the two events for the same write. And we say write ID equals write ID and row time between, the end row time should be between the starting row time and the start row time plus 1 hour. So we assume here that a write doesn't take longer than 1 hour, and obviously also the end event should not happen before the start event. So this is how you would express such a join. It's as you would declare it in a regular database, and then we can compute an average on the difference between the timestamps of end event and start event, and that way compute the average write duration per pickup location. So if we would build a dashboard with that, we could have simply ingest the data from Kafka into a Flink query running on Flink, materialize the result into Elasticsearch, and then display the result with Kibana. So this would be a pretty easy way to declare or to build such a dashboarding application. Yeah, so all of that sounds good, I hope. But how can you actually use it? At the moment, SQL queries must be embedded in Scala and Flink code in Flink. This is partially also because of the tight integration with the data stream and data set API. However, so far the community pretty much focused on the internals of the API. So we built the operators, type support, built-in functions, and extensibility for user-defined functions and internal catalogs. All of this is running in production at Alibaba, Huawei, and Uber, so proven at scale. And all of these serious users of these APIs build their own submission systems and connector libraries for getting data into the API, getting data out of the API, and having a nice user interface for their employees to submit queries to. Because nobody really wants to embed all the code, and nobody wants to write a Java class just to run a SQL query. So the community so far neglected these user interfaces a bit. There is no query submission client, no, CLI in a released version of Flink yet, no catalog integration, and the set of connectors for systems is also a bit limited at the moment. However, we are currently working on that, so we noticed that this is probably not our strong point, so we're putting more effort in developing these things. And there is a SQL CLI client coming in the first version in Flink 1.5, and Timo is now showing a demo for that.
Thank you, Fabian. So welcome everybody also from my side. So I have prepared a little demo of the SQL CLI client, but I have to always mention it is still in a very early phase, so it's a beta phase right now. Don't expect too much, but it's already a very, very useful tool, especially if you are developing a SQL query. So first of all, how does it look like? So beginning from the next release, you will have an additional binary in the normal Flink distribution. You can see it here. It's called Flink SQL Client. The Flink SQL client is a completely new way of also configuring Flink, because in the past we always had to configure Flink via the API, via the data stream API. From now on, we also have to support different ways. So what we are doing now is we have a YAML file, a so-called environment file, with which the SQL client can be configured. You can provide some default environment file. You can also have per session environment files, where you can define the table sources and things you want to use. So in this case, we have a taxi ride source. We define the schema, how the watermarking and timestamp conversion is happening, from where we want to read our table. In this case, it's Kafka in version 0.11, some Kafka properties. We also can configure the format. So in this case, we want to read a JSON format from Kafka. You can have execution settings, like in this case, we have a streaming environment, but we can also do a batch environment. You can select the result mode that you want to see in your CLI. Do you want to have the result presented as a table, or do you want to see the raw changelog that is coming out of your program and some additional deployment settings? So what are we going to do? Want to execute? So this is the example that Fabian just showed in the presentation. The nice thing about standard SQL, as you can see here, you can use any regular SQL editor. In this case, it's just Sublime Text. But since we are standard SQL, you can use your favorite tool for SQL editing and syntax highlighting, whatever. Since we are using also a non-Java project anymore, we also have to think about how do we add connectors or formats. So if we want to use the Kafka connector, how do we do that without setting up a Maven project anymore? So what we can do, we can just have a folder with a jar. So beginning from 1.5, we will provide jars for connectors and for formats. So you can just drag and drop your jars into a lib folder, and then we are ready to go. So let's start the SQL client. I already have a Kafka topic running. Here you can see I pass the clients that the libraries that we want to use on the client. As always, you can get help for the supported commands so far. You can list the tables that are available right now. In this case, it's just taxi ride, and then you can just execute a query like this. And as you can see now, we have a running Flink job here. It's a very simple one, but in any case, it's running, and we can also retrieve the results. We can change the refreshing speed. We can also pause the refreshing. So now we can look into our result. We can select a row. We can open this row and look into what we have programmed. So it's a pretty nice, useful debugging tool so far. So as I said, right now, it's a nice toy, but we have plans to do more serious things with this start. Some of you may have heard of it. We have opened a flip for that. So flip 24 describes the new way of submitting queries. We want to have a so-called SQL query service. So far, we only support select queries. In the future, we want to just also support insert into statements so that you can submit a job that just a regular Flink job that just syncs into a defined sync. But in the future, we will also want to support statements like create materialized view, which you then can access with additional query services, as in the next slide. So how does a query service look like? In the future, we might have something like a server that sits in the cluster. It is responsible for submitting the job to the Flink cluster, for submitting the query. So it receives the query, submits the query to the Flink cluster. It has access to external catalogs or schema registries, and it has a results server. So in most cases, you usually have clients that have no access to the cluster, or you don't want to give the applications full access to the cluster. So we will provide a way so that you can access the results via the query service while the Flink job is running. A nice thing is, since we are abstracting the result or the result from the application, we can also select where we want to push the data into. It can be an event log, it can be a database or HDFS, and the SQL query service then knows how to read from this external sources and can then provide the result back to the application. Another solution would be to do it a little bit differently, because in this case, as I said, applications do not need a special client. They can just access this REST API, but the problem is the query service can be a bottleneck. So actually what we want to have is that the applications can still run even though the query service goes down, right? So we imagine something like a serving library. This servicing library will get back just a handle to the result from the query service, so that the application can then access the event log or the database by its own. So the query service is just a submission client, and the application is standalone, basically. So far, this is just a flip and just a Jira issue. We are looking heavily for feedback because we want to design something very useful for a lot of users, to have a broader audience for that. So share your ideas, give feedback, discuss it on the Jira or on the Flink dev mailing list. So to summarize everything, we have a very useful core API already with a unification of batch and stream queries. SQL solves already a lot of streaming use cases and is also used by bigger companies like Alibaba and Uber. But there is much more work to do to make it even more easier to submit queries, to have nicer user interfaces. So get involved, join the discussions. Thank you. Any questions? Yes.
So the aggregate result is it stored as part of the state of the operator?
So right now it's just stored in the heap of the query service. But long term we can also think of something like a queryable state thing, where we can store it in state and then have I don't know if you are familiar with the queryable state feature of Flink, so that you can just directly access the state from outside, basically. So might be possible.
So if that node goes down, can I get the state where it was last processed, the last process state? Can I get back to that state?
So right now it's not. So this queryable state thing is not done. So it does not support exactly once guarantees or anything. So it's just to have an insight in the currently running application.
So can the SQL API being accessed programmatically from code?
Yeah, so basically that's at the moment the only way you can actually access it. As I said, you have to embed the queries into a Java class. So you have to set up some kind of like a streaming environment and a table environment, then you can register your tables in there, and then you can run a query on this table environment, get the result back, and write it out. So this is like the current way it's done. Adding these features like a query service or this CLI client that you just specify the query as a string and submit it. This is basically the new way. Does that answer the question?
So the follow-up question is, can I mix the higher level and the lower level APIs? For example, if I have an hourly aggregation job running, I want to submit the result, let's say, every minute.
Yeah, you can easily do that. So the SQL and table API is fully integrated. Can be mixed and matched with the data stream, data set API. So this is super easy. You can easily convert a table that has been compute it from a SQL query into a data stream, and then do whatever you want with the data stream.
Great, thanks.
If my requirement was basically join, so the join feature that you in SQL, does it join only streams, as in one stream of data with another stream and the data being in memory, or I can even do a lookup to some table and express that as a SQL query? For example, say my data resides in some key value store, and I have some data that is coming in as part of a Kafka stream, and I want to join these two data sets, basically a join on a key, some key, right? And then express the join output to some other database, right, or Kafka. So can that be described in a single SQL query right now?
That depends a bit on the requirements. So the join that we're currently supporting here are for streaming queries, streams on proper joins on proper streams. You can implement a join against a table that resides in a key value store you could implement that using a table function, for instance. Right now, the tables functions are internally implemented with, I think, a flat map function, so not using Flink's asynchronous function, which you, I guess, would like to use in that case. But this is a feature that can be more or less easily added. Yeah. So lookup against an external table is possible and can also be improved.
Quick question. For the SQL client, every query that you submit will create a new Flink job, right?
Correct, yes.
Okay. If I wanted to build, let's say, an application, a UI for the analyst in my company to run queries, is that the way to go? Do I need to create a single job for every query? Or is there a way to have like a Flink job that you push ad hoc queries to in?
I think it depends on the use case. So, I mean, right now, the goal of the SQL client is actually to submit a job to Flink and then have multiple, or have an easy way to produce or get data out of this running application. Yeah. So, I mean, ad hoc queries, you mean submitting ad hoc queries from your application, right? Will be a little bit difficult, I think. So, yeah, we will have to look into that. But first of all, we will support materialized views that you define in advance, and then you can maybe in the future query these materialized views with SQL. But yeah, we will see how this turns out.
Yeah, I mean what you're asking for is basically like something like multi-query optimization. So you have a set of multiple queries that are then ideally holistically optimized. You can share common path of the queries, right? So this is something that we're not supporting yet, and it's also not really on the roadmap. I can see that this is like a terribly useful thing to do, but it's also not an easy thing to do.
Does the SQL client know about the resource management? So how does it know how many task managers it needs to run the query and not fall behind? Or
no, this is completely up to you. So you define the parallelism, the maximum parallelism. So all the features that you usually would, or you have to define in a regular Flink job, it's just an easier way to submit your Flink job, or a programming-free way of submitting Flink jobs, basically.
Hello. So I have one question about the difference of the embedded SQL and the SQL client. For example, in the embedded SQL, I can break down a very complex SQL into several steps. Is it doable for the client? Like, I cannot write one logic in one SQL. I want to also do similar as the embedded SQL. First, run this subquery, and then run another subquery, and finally do run the last one based on the two subquery.
Yeah, I mean, in the long-term run, we should support something like that. I mean, right now, so first of all, we support subqueries, and we also support insert into queries soon. So basically, what you need to do is right now is you have to have some connector in between, like Kafka. So if you want to connect multiple Flink jobs together, you should go through a log, and then you consume this log again. This is how it works right now.
Yeah, but adding something like logical views shouldn't be too hard, I guess. So I think CalSite has probably support for that, so should be feasible to just register a virtual view in the submission client, and then when you define a query based on the virtual view, CalSite will just
Yeah, we could also think about
that.
adding the SQL query in the YAML file so that you can then see it as a table, and then it's just a view for the SQL client basically.
I had one question. So I saw that you support insertions and updates. You also support deletions, right?
So on the input side, currently we only support append queries. So this is what we're currently supporting. We're working with contributors to also support upsert queries. So per key, like when ingesting data from a stream into a table. Right now we only support appending. Upserting is on the near-time roadmap. On the output side, we support fully the full spectrum of like append, upsert, retraction. So when a query converts an append table, you can run any query that like modifies the table arbitrarily, so to say. You can somehow you can represent that in the output stream.
Maybe one more question, and then we have some lunch.
My question is there any constraint on the size of the materialized view?
So all the information that we're doing what the query actually is doing, a streaming query. It is incrementally maintaining a materialized view, right? So depending on how the query looks like, this means that you have to keep intermediate state, right? The state is stored in Flink's state backends, so it can be on the heap, it can be on RocksDB. So you can, if the query runs too long, you can also run out of space there. There are a few options to control this size. So if you have a key, if in this simple query that I've shown, like group by user count, if there would be a user that is inactive for some time, there is a way to configure a timeout that removes the state for this user.
If I do it using append and upsert, it's basically, I believe the upsert is updating the actual data, right? If I do append, it's going to be, appending more data.
It pretty much depends on your query, right? So I should note that creating a table in append mode does not mean that we materialize the table fully in memory. If you run a simple filter query on an append-only table, then no data is materialized. It's just a virtual representation. If you, however, run a query as this group by user count query, then also we don't materialize the full input table. We only materialize the counts per user. So it really depends on the operation, how much state it keeps. It's hard to give a general rule. We'll add some tooling for users to reason about the state of a running query, but it pretty much depends on the query. If you have a window query where you compute tumbling windows, you have to keep the state for the tumbling windows to maintain them, and when they can be closed, the state is also automatically removed. So Flink supports very large state. So we have users running jobs with terabytes of state. It scales out. The state is distributed. So you can. It depends on the query, I guess. But these queries can have very large state as well. Yeah. In the end, everything is translated into a data stream job that you could also write by hand. But that's a little bit more effort than giving a small SQL query.
All right. Thank you very much, Timo, Fabian.